Hey everybody, today I'm going to go over notes on limiting and excess reactants. These notes should be on my webpage if you want to check them out there. Alright, so limiting and excess reactant. Those words kind of tell you exactly what that means. A limiting reactant, if you look on the screen here, is the chemical substance that runs out first in a chemical reaction. This is the chemical that determines how much of the products are made. A limiting reactant is the reactant when you're doing a chemical reaction that is the one you're going to run out of first because it doesn't have as much as the other one. Okay? The true amount of your excess reactant is also determined by the limiting reactant. Excess reactants are all the other reactants in a reaction, chemical substances that you have more than enough needed for the reaction. So in a reaction you always have reactants and products. Okay? One of those reactants is always going to be limiting. The other reactants are going to be excess reactants. However many there are, they're excess. One of them is limiting. Okay? We can show a good example of this by thinking about how a tricycle is made. Now you guys all know what a tricycle is. A tricycle is a small kid's toy. It has a handlebar, one seat, 3 wheels, 1 frame, 2 pedals. Like this. Those are all the parts you need to make a tricycle. Okay? So I want to write that kind of like a chemical equation. If you have 1 handlebar plus 1 seat plus 3 wheels plus 1 frame plus 2 pedals, you end up with 1 handlebar, seat, wheel 3, FP2, or 1 tricycle, basically. Alright? So if you had 30 of each of these things to start with, if you went into a factory and found 30 of each of those pieces, answer these following questions. How many tricycles are going to get built? Well, if you think about it, if you have 30 wheels and 30 of everything else, but you need 3 wheels for each 1 tricycle, which is why it is a 3-to-1 ratio. So if I look at that, it is a 3-to-1 ratio of wheels to tricycles. Then if I have 30 wheels, I can only make 10 tricycles, keeping the same ratio. So how many tricycles are going to get built? Well, obviously we can only make 10 tricycles. Alright? So, because of that, and because everything else takes less, pedals takes 2, and everything else takes 1, there and there, all of those are only going to need to use a smaller amount. Pedals, you're going to have to use 20 to take 10 trikes. If you have 10 trikes, that's going to be 20 pedals, and 10 of all other parts. So, because of that, how many handlebars are you going to end up using? You're going to need 10 handlebars. You're going to use 10 seats. You're going to use 30 wheels. You're going to use 10 frames. You're going to use 20 pedals. So the item that's limiting factor is the wheel, because you're going to run out of those first. It takes more wheels in this reaction. It takes 3. So the wheels are your limiting factor. Obviously this is pretty simple reaction, but for another good example, there's one that my students do in class, that you guys do in class a lot, and that's when you take a magnesium ribbon and you burn that magnesium ribbon in the presence of oxygen in the room, and that creates a white powdery substance called magnesium oxide. Okay, so I need a 2 there and a 2 there to balance that reaction out. Alright, so when you guys do this reaction in the classroom, you're taking a small thin strip of magnesium, about that big, and you're burning it in the oxygen. And once you burn it, you create a white powdery substance, magnesium oxide. There's your white powdery substance. I know it's blue, just it's white. So what determines how much magnesium oxide that gets made? Is it the oxygen or the magnesium? You got to figure out which one you're going to run out of first. Are you going to run out of magnesium or run out of oxygen? Well, since we could still breathe after you guys burned the magnesium ribbon, that means you ran out of magnesium first. There was a bunch of oxygen, tons of oxygen left over in the room. So this is always going to be excess, especially if you're doing it just in regular air. This is limiting, because once this piece of magnesium is gone, then the oxygen is not going to have anything to react with, even though there's more oxygen left. So this limits how long the reaction is going to go, and the amount that you start with is directly responsible for the amount of product you're going to end up with. And this is why the limiting reactant ultimately determines how much product you get. Okay, so let's do a chemistry example to figure this out. Okay, so I've got a chemical equation. PbNO32 plus Ki results in PbI2KNO3. Alright, so I'm going to write that out on the top. Lead nitrate plus potassium iodide results in lead iodide and potassium nitrate. Okay, so when I'm doing the reaction, I'm going to actually create a little bit more space here for me. There we go. So when I'm doing this reaction, I start with these products and I end with I start with these reactants and I end with these products. Okay, balancing. You got to check and make sure. Always on stoichiometry problems, check to make sure they're balanced first. They're not quite balanced. I got 2 I's, so I need a 2 here. Now I have 2 K's, so I need a 2 here. So I have 2 nitrates, lead, lead. Okay, so using the balanced chemical equation, we can answer these questions that are on the screen. The first question is, which substance is a limiting factor when 2.96 grams of lead-2 nitrate reacts with 3.22 grams of potassium iodide? Okay, so I've got 2.96 grams of lead-2 nitrate, so 2.96 grams of that guy. I also have 3.22 grams of potassium iodide, so 3.22 grams of that guy. So I have to figure out which of those two is my limiting reactant. Now I can't just look at the grams and compare and say, oh, this one has less grams, so it's limiting. Because there's two things that are going to decide what really matters here. The first is, these have different molar masses. So the difference in grams is not as close as you might think, because there's actually a big difference in the moles. Okay? And moles is what we compare when we're looking at chemical equations. If you look at the chemical equation, it says 1 mole of lead nitrate plus 2 moles of potassium iodide will result in 1 mole of lead iodide and 2 moles of potassium nitrate. Okay? It's not talking about grams with these 2's and these 1's. The coefficients are referring to moles. So I've got to figure out how many moles I have, and then I've got to figure out how many moles of the products I'm going to end up with to figure out which one is the limiting reactant. So basically what you're going to do is this. You're going to do the same equation twice. You're going to determine how much of one of these two reactants will this amount make, and then how much will this amount make if I react them by themselves. So if I react this amount with an unlimited amount of this, how much will I make? If I react this amount with an unlimited amount of this, how much will it make? Figure out which one makes the least. Whichever one makes the least product is your limiting reactant, because when these two react together, they can only make as much as whichever one is making the least product. Okay? So, I'm going to use this product to figure it out, because this has a coefficient of 1 instead of a coefficient of 2, which means the calculations for this one will end up being easier. Alright? So, to set up the reaction, or the equation rather, you start with this one first. 2.96 grams of lead-2 nitrate. Okay, I need to convert that into moles of lead-2 nitrate. So grams of lead-2 nitrate will go down here. Can change that to 1 mole lead-2 nitrate. Alright, so this is the molar mass, because you're going to get rid of the grams and replace it with moles. I calculated the molar mass of all these compounds earlier. So lead-2 nitrate is going to be 331.28 grams per mole. Remember, in order to calculate your molar masses, you're just adding up their masses from the periodic table of elements. So I just took the mass of the lead, 2 nitrogens, and 3 oxygens, and added them up, and that's what you get. Okay, so 331.208 is what I'm using. .208 grams and 1 mole of that. Now that I've converted this number into moles using this conversion factor, I'm going to use another conversion factor to convert from moles of lead nitrate into moles of PbI2. If I look at the coefficients, it is 1-to-1 ratio. So these units cancel, these units cancel. So the math here is 2.96 divided by 331.208 times 1 times 1 divided by 1. So I don't need to worry about the 1. So it's just 2.96 divided by 331.208. So, calculator. 2.96 divided by 331.208. Okay, I have 3 sig figs here, so my answer needs to be in 3 sig figs. 0.00894 moles of PbI2. So if I completely react this reactant, that much of it, I will end up with that many moles of product. Okay? Now let's do the exact same conversion, but this time using this reactant. Okay? So I'm going to take 3.22 grams of Ki times 1 mole of Ki per the molar mass in grams of Ki. And Ki is going to be 166.002 grams per gram. 166.002. Get 1 mole of PbI2, because the coefficient is 1, for every 2 moles of Ki, because the coefficient is 2. So moles of Ki will cancel, grams of Ki will cancel, so I'll be left with moles PbI2. So the math on this one is 3.22 divided by 166.002 divided by 2. Okay, so clear that out. 3.22 divided by 166.02 divided by 2. So 3 sig figs again, so 0.009698 will be 970 moles of PbI2. So if I look at both the amounts that I just calculated, then I see that this one ends up with a smaller number, which means if all this reacts, it'll make this amount of moles. If all of this reacts, it'll make this amount of moles. This one is smaller, so because of that, this guy is limiting. This reactant will run out first, because this could make more, but it can only make as much as whichever one's going to run out first, and this one's going to run out first. So up top here, green, I'm going to write limiting on top of that guy, and excess. So I remember which one is which. That's limiting, that's excess. Okay, so there's all the work for that. Alright, so that's question 1. Luckily, this is the hardest part of the problem. So after that, now that you've found out which one's the limiting reactant, I know this amount is what I'm going to be starting with. And this number in red of moles of PbI2 that I'm going to end up with is the product I'm going to make. So I can use those to figure out my other 2 questions. Question 2 says, how many grams of the excess reactant will be used during this experiment? So I'm just going to slide that guy up a little bit there. This guy right over me. I'll put him right on top of the blue. I don't need the blue anymore. Okay, so I want to know how many grams of the excess reactant am I going to end up with. Okay, so how many grams, and if we look at the 2 reactants, the excess is Ki. So how many grams of Ki will be used during this experiment? So how many grams of Ki did it take to equal the 0.0084 moles of PbI2 that are going to get created? In order to calculate that, all I got to do is do the exact same calculation I did for Ki here, but I'm just doing it in reverse. I'm going to start with moles that the limiting reactant gave me, because that's how many moles are actually going to get made. So I'm going to start with that number and do a conversion of moles of this to grams of that. So It's another two-step conversion, just in the opposite direction. Okay, so 0.0084 moles. Oh, sorry, 894. 94, my bad. That number. 94 moles of PbI2 times 1 mole of PbI2 on the bottom. This is my molar ratio from the reaction. For every 2 moles of Ki that get reacted, 2 right there, times the molar mass, 1 mole of Ki, and then the molar mass of Ki was 166.002 grams of Ki. So moles of Ki cancel, moles of PbI2 cancel, so it's 0.00894 times 2 times 166.002. 0.00894 times 2 times 166.02. So that equals 2.96 grams of Ki. That's how much I'm going to use. I had 3.22 grams, so I do end up with some excess. Okay, I used 2.96. Oh, actually, it's 2.968, so I need to round that to 2.97 grams. That's how much I end up using. Okay, the third and final question says, how many, when the reaction is complete, how many grams of lead-2 iodide will be created? Now this one is pretty easy because I've actually already calculated how many moles I'm going to end up with of PbI2. So to figure out how many grams of lead iodide will be created, all you got to do is take the moles of PbI2 that I'm going to end up with that I already calculated and change that into grams of PbI2 that I'm going to end up with. So just take the moles of PbI2. That's how much is going to be made. Now all I only need to do is multiply that by the molar mass of PbI2. So there's a certain number of grams of PbI2 for 1 mole PbI2, and that certain number I calculated earlier is 461.008. 461.008. 6. So moles PbI2 will cancel, and that'll give me grams PbI2. So move that up a little bit. 0.00894 times 461.008 is 4.12 grams PbI2. So that's how you solve these problems. Really, none of the math is actually anything new. It's just the concept of having the limiting reactant and figuring out which reactant is minimum. So remember, to figure out your limiting reactant, you take the amounts that you're given to start with, and then you convert them from grams of whatever you started with to moles of one of your products. Okay, it doesn't matter which product, you choose which one. I always do one that has a coefficient of 1 if I can. And then convert both of them, and whichever one makes the least amount of product, that's going to run out first because it's making the least. That is your limiting reactant. And then all of your numbers after that will be based on the limiting reactant or the number of moles that you're making a product from the limiting reactant. Okay? Hope that helped clear things up for you guys. Talk to you later.